All right, so points on the curve, y equals 2x cubed minus 3x squared minus 12x plus 20. Okay, and we want to know the points on the curve where the tangent is parallel to the x-axis. All right, well, they said tangent, so when they talk about tangent, they're talking about a derivative. So dy dx is one way of noting a derivative. Instantaneous change in y with respect to an instantaneous change in x. There's a delay. It looks beautiful on my board. I don't know what's going on here. Yeah, and I'm up to 53 seconds. Yeah, okay, now it finally clicked in. All right, so the derivative here, we can apply the power rule and come up with 6x squared minus 6x minus 12.
It's really like laggy.
Yeah, there we go.
There it is.
All right. All right, so the part where it's parallel to the x-axis. All right, so parallel to x-axis. All right, what kind of lines are parallel to the x-axis? Horizontal. And the slope of a horizontal line is 0. All right, and so what we're getting at here is the idea that our derivatives, at whatever the appropriate points are, maybe there's only one point, maybe there's no point. Our derivative should be 0 at any location in which the tangent line is parallel to the x-axis. So after all that, it's really just telling me to set my derivative equal to 0 and solve. All right, constant multiplier of 6, so let's kill that. Oh boy, it'll happen. It's getting there.
Almost there.
Trying to use the board. Oh, pointing at the wrong thing.
Just wait over the marker. And then wait for it to appear.
Maybe just like swipe up on it and start a new.
Possibly. I'll have like show and tell. It'd be like I write something and then it's like, and then I write something out like kindergarten, and I show it. I don't understand.
There's like a loose cord somewhere.
Yeah, I don't know that the internet necessarily works that way, but.
I mean, it's like because if it's connected to the Apple TV thing, and then it's like going to the projector, it could be that.
I think it's
Or
a
it's
classic
just
restart
bad, like,
situation.
yeah.
All right. Well, anyway. So this is what's going to happen. I'm going to start writing it, and it's going to pop up. No. Okay. So anyway, we need to solve this.
Yes.
Algebraically.
So you can tell it's not working because on the timer there it says 3:45.
Yeah, and I'm up to 4:07 right now.
That's 20.
It's one frame every 20 seconds. 3:30.
Severe delay. Well, anyway, our factors would be x minus 2, x plus 1. And so we get x values of 2 and negative 1, right, which will eventually appear on the big screen. All right. It does beg the question of whether or not we need the full-blown coordinates, or do we just need the x values of the coordinates. So it says find the points on the curve. So, oh yeah, this is just outstanding. Let's see. Oh, well, actually, it seems to be working now. So if that's the case, maybe you want to use little algebraic shortcuts like, I don't know, the remainder theorem to get your solutions, rather than doing direct substitution. In this case, subbing in a 2 and a -1 is not difficult. Hopefully you don't find it to be difficult. But, you know, if I had to substitute an 11 in or something like that, then it could be, you know, it could get out of hand pretty quickly. It's going to be an easier ride if you use the remainder theorem in almost all cases. So let me just review that real quick. And this is something that I'll come back to over and over again throughout the course, because when we get to AP review and you come across a problem on the non-calculator portion and you're like, how the heck am I supposed to do this on my calculator? Except you probably wouldn't, without a calculator, except you probably wouldn't say heck. Yeah, people get emotional when they start seeing the kinds of curveballs that the College Board likes to throw at you. Yeah, things like this, I don't want it to be foreign to you. I want you to be like, oh yeah, of course I would do that. So, remainder theorem is telling us that if I want to evaluate the function, all I need to do is run whatever the number is, in this case a 2, through synthetic division and just take note of whatever the remainder is. All right, so 4, 1, 2, -10. Well, that's fun. -20, 0. All right, so we're looking at f of 2 is equal to 0. And then do the same thing with a -1.
Why did you use the same numbers and not the second round of numbers?
Because the remainder theorem works off of the original polynomial. So what I'm doing here is equivalent to finding the y value associated with an x of -1, but for the original function, not a simplified version of it. All right, so barring any catastrophic error, I mean, it's a weird number, so I'm second guessing myself, so I'll double check in a second. But I'm getting f of -1 equals 27. So it's telling me that I have horizontal tangents at the coordinates 2, 0, and -1, 27. So you got the derivative equal to, you said, 3x squared minus 3? And then you substituted, it was 2, yeah, x equals 2. Just a word on notation. If you want to use the dy dx notation, showing the substitution of a particular value for x is kind of like the way the calculator writes things. So dy dx, the vertical line always means such that or given that. All right, so dy dx such that x equals 2. All right, so that's the proper notation for a substitution into the derivative if you're using the dy dx. So 3 times 2 squared minus 3, and that gives us what, 9? All right, so this is the slope of the tangent line. All right, yeah, so that's the key ingredient. So understanding that, derivative, instantaneous rate of change, all well and good, but it all comes down to the idea that you have a particular line that is tangent to the curve at a particular point, and it will have a slope, and we just got that slope. Now what we're looking for here is the equation of the line perpendicular to that. So I'm not going to draw the actual function, I'll just draw something generic. I mean, that could very well be something along the lines of it. This would be my tangent line, so this is my dy dx. It has a slope of 9 at that point. What I'm looking for at this same point is a line perpendicular. All right, also known as the normal. The normal line. Okay, so the slope of the normal, if it's going to be perpendicular to the tangent. Perpendicular lines, what's the relationship? Negative reciprocals. All right, so negative reciprocal of 9? Negative 1/9. All right, so now I know the slope of the normal line. They want the equation of the normal line, so I will use the point slope form of a linear function. All right, y equals m times x minus x of 1 plus y sub 1. I have the slope. They gave me the point. They actually gave me the y value too. They told me at the point 2, 3. So I'm looking at y equals negative 1/9 x minus 2 plus 3. All right, so the relationship is that they're negative reciprocals to one another. And then we use that to go full-blown algebra 1 on it. That's the key. Don't lose sight of the fact that, and that's what I was trying to point out before, a little bit of calculus in there. And that's how it's pretty much going to play out for just about everything. We'll do a setup, we'll do a smidge of calculus, a whole lot of pre-calc, and then come up with a final answer, and that's really how it goes. Now, the little bit of calculus part of it, it could be a little bit of really difficult calculus, but it's usually just a single step that is calculus based. All right, so that's why calculus can be pretty challenging, because of all the non-calculus stuff that works its way into problem solving. Right, because it requires that you have pretty good mastery of all the pre-calc stuff. And I don't mean stuff from the course called pre-calc. I mean the pre-calculus stuff, aka every mathematical concept that you learned prior to this year. That's pretty daunting when you hear it that way, I think. Oh yeah, very inspiring. They're like, oh yeah, I did really well in pre-calc. Yeah. Okay. What about that obscure topic from like the first week of Algebra 2 honors? You know, it's like, well, that's going to work its
The
way.
imaginary separation thing? That's what our first topic is.
Well, that's the one. It's the one good thing is that you won't have to deal with imaginary stuff in here. Oh, well, in this course, it isn't until. I mean, you got to get through multivariable before you start working imaginaries back in.
Like, why use imaginaries? Like, what?
Like, what's the point?
So we don't want to do this right now.
Why could coming up with an imaginary number actually help someone?
So
It's a very good question.
it is a good question. So the idea is that in certain applications, when you take the square root, you could have the square root of a negative number, but we don't really use in the physical world. We don't really use imaginary numbers as entities in and of themselves. We don't say, okay, I'm going to imagine that we have. It doesn't really work that way. It really just implies direction. So if you're talking about, I don't know, movement along a circuit, it's a vector quantity. If you have a negative under a radical, that just means that your vector is moving in a negative direction. So when you pull out the eye really just kind of draws attention to itself as something that's moving in the opposite direction. So we're not really looking at anything related to the value of I itself, more so what the I represents. And that's really, in the physical sense, really all there is to it. But then you get into some abstract things, but that's purely mathematics, where it's like you're pursuing academia. You know, it's like I'm exploring math for the sake of exploring math. Like that's when you start looking at the graphs of imaginary numbers and things like that, the abstract viewing. I'm trying to remember. I think there was a video that I saw. I think it's imaginary number intuition.
Why do you use white? Every year. It's been had several times.
I think this is
Sophomore year. We worked hard. I tried to get that done.
You're in KVH, right?
Barely.
Yeah, I'll save this. We'll watch it one day on a Friday where I don't feel like doing anything.
I've only one.
But yeah, there was a really cool video that talks about like the graphs of imaginary functions and like how you can conceptualize them. It's pretty cool. So we'll tackle that at some point just for fun, I think.